In this video, we're going to talk about exponential and logarithmic functions and how to take their derivatives. And so we're going to add more rules based off the type of function that we're going to be dealing with. And so the exponential rule has to do with taking the derivative of an exponential function. Remember, your exponential function, you have a base that is a constant, like a number. We use a in this example, as you can see here. And your actual input variable is your exponent. When your function looks like this, remember we have that derivative formula. Well, you don't remember this because we haven't gone over it yet, but f prime of x is going to equal a to the x times the natural log of a. Remember, when we have these derivative functions, f prime of x actually equals the limit as h approaches 0 of your difference quotient, which is very similar to your average rate of change formula. But this is what's allowing us, so if I apply that formula, that limit, to an expression that looks like this, that limit is going to equal this thing right here. And what we're going to do in this class is we're not going to focus on doing this limit, even though it's sitting in the background. We're going to focus on looking at and using these formulas here. And so when I have the derivative, when I want to take the derivative of an exponential function, its derivative is a to the x, that base to the x times the natural log of the base. And so for instance, in this example, my input variable is x, my output variable is y. If I want to find my derivative with respect to x, that's dy dx, or you can say y prime. So some people may say y prime equals, some people may say dy dx equals. Different notations, they mean the exact same thing, the derivative. My base here is a, my variable is my exponent. So by my derivative of an exponential rule, that's 5 to the x times the natural log of 5. In part B here, we have y equals 7 times 10 to the x. We just have a constant multiplied by our exponential function 10 to the x. In the last video, we went over how to take the derivative of a constant multiple. The constant stays in your derivative. And so if I want to find the derivative of this function, it's going to be dy dx equals my constant times the derivative of my exponential function, 10 to the x times the natural log of 10. That's my derivative. Let's go to part C. F of x equals e to the x. Remember, e is your natural exponential function. E to the x is your natural exponential function. E is a number, 2.718, so on and so forth, right? And so this is exactly the same as seeing this 5 to the x, except since that's an irrational number, we use the letter e for that. But my derivative is f prime of x. It's going to be my base to my exponent times the natural log of my base. Now, what we know is that your natural log and your e are inverses of each other, so they cancel each other out. So that's the natural log of e. When they cancel out, since it's multiplied by e to the x, that's 1. And so this simplifies to just e to the x. So the derivative of e to the x is e to the x, which is pretty cool. And then last but not least, my output variable here is p. My input variable here is x. When I do my derivative, I can call this dp over dx. Again, some people may say that that's p prime, but it's a constant multiplied by exponential function. So I write my constant. I multiply it by the derivative of my exponential function, which is 1.1 to the x times the natural log of 1.1. And that is what my derivative equals, and that's how I'm going to write it, all right? In addition to finding the derivative of an exponential function, we can also find a derivative of a natural log function. The derivative of f of x equals natural log of x is f prime of x equals 1 divided by x. Again, this comes from that limit as h approaches 0 of f of x plus h minus f of x all over h conducted on this function here. F of x equals the natural log of x. You do this work, you end up with 1 over x. We're not going to focus on doing this work to get to that formula. We're just going to use the formula. And so in part A, I have f of x equals the natural log of x minus 2. Notice this is two separate terms separated by a minus sign, right? And so when we do the derivative, it's going to be f prime of x. We can do the derivative separately for each one of these. The derivative of ln of x is 1 over x. And the derivative of 2 is 0, and so this just equals 1 over x. Let's go to part B here. I have f of x equals 3x squared minus 5 times the natural log of x. I'm going to, again, since they're separated by a subtraction sign, I'm going to do the derivative separately. So this is going to be f prime of x equals, well, this is a power rule with a constant multiplier, so that'll be a 3. I bring that 2 out front, so that'll be a 6x to the 2 minus 1 power, or the first power. I'm going to leave off that 1 as that exponent. And this is a constant multiple of our natural log function. So when you have a constant multiplied by a function, your constant stays multiplied in your derivative of that function. So that's 5 times 1 over x, because the derivative of natural log, as we just saw up here, is 1 over x. Now, sometimes you want to write this. 5 is 5 over 1, and so I can write that as 5 over x. And we can leave that simplified in that manner. All right, this example just has a bunch of functions. We have 1, 2, 3, 4. You can think of that as the sum and or difference of 5 separate functions, right? But we can do the derivative separately. Now, I'm going to add something here. I'm going to say plus t squared, okay? Now, notice here is f of x. My input value is x, right? The reason why I want to put this here is because I know a lot of times we use t as our input variable, but pay close attention to your input variable here is x. That means if I see any other variable besides x here on this right-hand side, it is a constant. It represents a number, so treat it like a number, right? And so when I do the derivative here we have our exponential rule, exp. Here we have our power rule. Here we have our natural log rule. Here we have our constant rule. Here we have our exponential rule. And here we have our constant rule again, right? Because that is not a function of x, it is a t, right? So f prime of x is going to equal, okay, the derivative of exponential. Well, we saw that the derivative of e to the x was e to the x. Now, if you didn't want to think of that and just use the exponential rule, it's 4, which is a constant multiple, times e to the x times the natural log of e, right? Then we go to this one, I get a 12x squared because you bring that 3 out front. 3 times 4 is 12. You reduce that exponent by 1, you get 2. The derivative of a natural log is 1 over x. The derivative of 2 is 0. The derivative of an exponential, again, that's 1.9 to the x times the natural log of 1.9. And then the derivative of a constant here is, again, 0. And so I have that derivative right there. All right, and so I can clean this up a bit. The natural log of e is just 1, and I don't need to write those zeros there. And so my derivative is going to equal 4 times e to the x plus 12x squared minus 1 over x minus 1.9 to the x times the natural log of 1.9. And that, my friends, would be your simplified derivative in that example. All right, we can find the second derivative by doing the first derivative first. The derivative of e to the x is e to the x. So we know that it's e to the x times the natural log of e, but every single time the natural log of e is going to count. So I'm going to stop writing it, all right, now that we know that fact. All right, the derivative of natural log is 1 over x. The derivative of x squared is 2x, and the derivative of pi is a number, 3.14, whatever, and that derivative will be 0. And so what I have here is y prime equals e to the x plus 1 over x minus 2x. Our goal is to find y double prime, right? Well, for me to find y double prime, I need to rewrite this 1 over x. So I'm going to rewrite the 1 over x. Now, I have the power of erasing it here. On your paper, you might want to write this in a different step so you know what we did. I'm going to write that as x to the negative 1 power. Because if that's 1 in the denominator, then if I bring it out of the denominator or do its reciprocal, it's going to be a negative 1 exponent. So now I can do y double prime. The derivative of e to the x is e to the x. Now when I do this derivative, it's a power rule. So it's going to be plus a negative 1. And if I subtract 1 from that original exponent, negative 1, I'm going to get negative 2. And this is the derivative of a linear function, which is its slope, which is the number there, right? And so if I clean that up, I'll have y double prime equals e to the x. Instead of saying plus a negative, I'm just going to write it as a minus x to the negative 2 minus 2. And that could be my answer. This answer is satisfiable. If you don't want to use the negative exponent, you can go the extra step. You don't have to in this specific course. Not right now, at least. Let's look at an example where we actually apply the derivative to a function. And I'm going to end up using my calculator because this is an application example. I'm going to move some things over ever so slightly so that we can do the problem. All right, it says the value of an automobile purchased. Um, Give me 1 second. I'm not prepared apparently. Um, the value of an automobile purchased in 2008 can be approximated by the function v of t equals 35 times 0.85 to the t, where t is the time in years from the date of purchase, and v of t is the value in thousands of dollars. Evaluate and interpret v of 4. Well, v of 4 is nothing more than evaluating that function at 4, right? And so what we can do here is say v of 4. That means we go and we plug in 4, where we see our input variable. And in our calculator, this is probably going to be a decimal. I'm going to round it to 3 decimal places, but I'm going to have 35 times 0.85 raised to the 4th power. I'm going to press enter, and that's approximately 18.270. 18.270. So I'm going to say 18.270, and that's going to be my units. This is the value of the car in thousands of dollars. So it's 18.270 thousand, and I put my dollars right here. If you want to write the word dollars, thousands of dollars, $1,000 there, you can, but I put my dollar symbol here. All right. So I'm going to interpret that, right? So my input value is the time in years from the date of purchase. Well, it was purchased in 2018, so I can be as specific as the year. And so I can say, well, 4 years from 2018 is 2022. I can say in 2022, the value of the car will be approximately 18.270 thousand. Okay, or that's 18,000. And if you didn't want to use all those units, $18,270. All right, that's an interpretation of that. It says find an expression for v prime of t, including the units, right? So v prime of t is the derivative of your value function. So v prime of t would equal, well, this is a constant multiplied by an exponential function. That's 35, and that's a constant multiplied by, so that 35 is going to be in there. And then the derivative of my exponential function is your exponential function. So 0.85 to the t times the natural log of 0.85. All right, I'm going to leave that there. I'm not going to multiply the natural log of 0.85 by the 35 because it's going to give me a decimal and it's going to be a rounding. All right. The units here is your units of your input divided by your units of your output. R is dv over dt. My output variable is v. My input variable is t. The units of v is your value, which is $1,000. And my time is in years, so I'm going to say per, not time, but year. Time is your variable, but year is the units, all right? And so that's the derivative, and that's the units of the derivative. And so now what we're going to do is we're going to evaluate and interpret v prime of 4. Well, v prime of 4 just means go to v prime, which is here, and plug in 4. And so I'm going to go back to my calculator, and I'm going to have that 35. And I know I already had it typed, so if you want to kind of copy and paste that, but I'm just going to go ahead and type it in here. Raised to the 4th power, and I got to go over, and I'm multiplying that by the natural log of 0.85. And I get approximately negative 2.969. Approximately negative 2.969. Now, I'm going to forget that when I write that, but negative 2.969. All right, and that's going to be $1,000 per year. And so we have a couple ways that we can to interpret that derivative, and this is how I'm going to do it, right? So it's an instantaneous rate of change because it's at the value input value of 4. So I'm going to say in 2022, the output, the value of the car is, since that's negative, I'm going to say decreasing by 2.969 thousand dollars per year. All right. Or I can say from 2022 to 2023. All right, I'm going to do it a little bit different. If we increased the number of the year from 2022 to 2023, 1 year, we can expect the value of the car to decrease by 2.969 thousand dollars, right? So over that 1 year, right? Or we can say from 2022 to 2023. I was trying to make it consistent with some of the stuff that we did before, but it's in years. So if I increase by 1 year, that's from 2000 to 2023. Or I can say over the year, from 2022 to 2023, we can expect the value of the car to decrease by $2.969 or $2,969. All right. Those both work as your interpretations of your derivative. By the way, remember this is an exponential function. The initial value of that car is 35 and it's in thousands of dollars. And it's decaying at 15% per year, right? From that stuff from chapter 1. Anyway, this is the end of this video. We'll get to some more rules when we start our next video. So hang in there. I'll see you next time.